Even the most sophisticated automated systems can paralyze themselves during a routine operation. When a physical instruction conflicts with an environmental reality, the machine often enters a high-speed vibration, caught between its code and the physical world. This happens because standard autonomous agents are built on a single loop cycle. They perceive their surroundings, interpret that data, generate a plan, and then act. When the environment presents a problem the agent cannot resolve, it hits a cognitive impasse. Its internal planner either times out or returns an empty set of possible actions. The standard software response to an impasse is a simple exception catch. The system retries the exact sequence that just failed, resulting in a repetitive, predictable stall. These agents possess complex models to evaluate the external world, but they lack any internal representation of their own cognitive health. They can see the terrain, but they cannot see their own logic. Without an internal model, standard exception handling leaves a fatal blind spot. The agent can record the failure, but it cannot diagnose why its own reasoning produced that failure in the first place. This architectural flaw creates a state called hypercanalization. The agent falls into a pattern of executing low-yield behaviors under tightening resource constraints, expending energy without achieving any forward trajectory. Because the agent is still processing data and attempting actions, its internal metrics suggests it is problem-solving. In reality, it is burning compute on a static environment that its current policy cannot navigate. The failure state is a direct result of the system adhering perfectly to its original code. The machine is following its logic to a fault, executing its programmed instructions even as they yield zero progress. A single-loop system lacks the hierarchical perspective needed to step outside its own execution. It has no mechanism to observe the loop from the outside and force a change in strategy. To break these infinite cycles, the software must utilize a dual-cycle architecture. This design treats the system's own internal logic as a controllable environment, allowing the agent to observe and modify its own thinking. The solution is a 6-phase metacognitive skeleton layered above the host application. The meta layer follows a parallel cycle: monitor, interpret, evaluate, intend, plan, and control. This maintains strict separation, functioning exclusively as a separate thinking checkpoint for the system's own processes. Data flows strictly upward. The monitor phase ingests execution traces to see how object-level modules perform. The return path is equally disciplined. Typed control actions flow downward from the control phase back to the host application to guide its next move. Each phase owns a distinct data transformation, preventing reliance on ad hoc patches. The monitor phase evaluates per-module expectations against specific runtime bounds. By utilizing this rigid structure, the system produces concrete typed signals, defining exactly where internal cognition has drifted. To detect a cognitive loop, the system tracks allostatic load. This diagram compares a flat line for environmental change, tracking how much the external world actually shifts, against a spiking line for the internal failure rate. If internal failures climb while the environment remains static, the system is hypercanalized. As failing cycles continue, the system accumulates bandwidth debt. Crossing the insolvency threshold formally signals the current policy is computationally too expensive to continue. The system's first intervention is dropping prior confidence, forcing it to consider alternative hidden paths. If the stall persists, the meta layer clears stale working memory, preventing old data from influencing new plans. Tracking bandwidth debt quantifies the compounding cost of a failing policy, signaling exactly when a strategy has become a physical liability. The transition to recovery is managed by the Discrepancy Resolution DTO. This table maps 4 sequential fields: symptom, explanation, goal, and plan. First, the monitor phase populates the symptom field with raw data, like a planner timeout. The explanation engine matches that symptom against hypothesis templates to identify the cause, such as a flawed behavioral policy. This explanation is converted into a typed goal, creating a proactive command to replace the active planner. Finally, the system generates a plan containing specific technical steps to restore cognitive health. These structured templates ground the explanation engine, ensuring causal hypotheses remain testable and preventing ungrounded justifications. transforming WA failures into causal explanations moves the system beyond reactive error catching toward goal-driven autonomy. Once the meta layer has a plan, it passes through the evaluate and intend phases before reaching the final control phase. Before the meta layer can intervene, it must clear the right guard. The control phase emits a typed control action packet, which hits this gated permission barrier. The right guard is a rigid safety boundary. It requires the metacognitive layer to request permission before any state in the host application can be modified. The control action DTO contains specific safe interventions, such as pausing execution, swapping out a logic module, or relaxing constraints on an active goal. The metacognitive layer strictly recommends these interventions. It never silently or directly overwrites the host's primary logic without this explicit handshake. This separation between the decision to change and the execution of that change ensures architectural safety, preventing the risk of uncontrolled self-modification. The system's trajectory is now complete, escalating from a stalled loop to load detection, then through causal explanation, and finally resolving as a gated, safe intervention. A system with metacognitive control identifies the specific logic branch causing the stall and replaces it with a viable alternative, allowing the operation to continue. This modular adaptation prevents the brittle, repetitive failures that characterize standard, single-cycle autonomous agents. Autonomy is built on the capacity to separate world anomalies from cognitive anomalies, enabling a system to safely reevaluate its own